Hey calculus class, some of you have asked, like I did last week for the 3-4 homework, some of you asked for more detailed notes on 3-6 and then extension of the 3-6, so I did that. So it's now due the same day 3-4 is, the day before the chapter 3 quiz, to give you some more practice with chain rule. So if I am using this notation, what this is saying is y is some function of u, and u is some function of x. And what this is telling us to do is to find the derivative of y with respect to x. You've got to take the derivative of the outer function, right? So this is going to go in here. We're taking the derivative of that and leaving the g alone, not messing with it, and then chaining on the derivative of g. So let's look at this example with sine to see how it's going to work. Now let's take this example with the sine function and this line to see how it works. So notice here I got this y is the sine function. So there's our sine function that's going up and down. And then I've got u in here. Now I'm going to type in this other equation, but then I'm going to pause it so we don't see the graph. Alright, so this variable inside u is going to be 3x minus 1. So if I write it, I get two graphs. One is the green, 3x minus 1 is just a line. I'm calling it u equals instead of y equals like we normally see, but it doesn't matter what we call variables. They can be anything. But notice what happened there when I take that away, I get the regular sine function. But when I put it back there, it gets squeezed in, and that's because of what this is doing to that graph. Literally what we're doing is we're replacing that inner variable with 3x minus 1. Alright, if it were just x, it looks like the sine function. But that 3x is squeezing the graph in horizontally. So just so you can see it, if I got the sine of bx, the b will squeeze this thing in the bigger and bigger that it gets. So it's squeezing everything in because that number is bigger than 1. If it's 1, it's the sine function. But the bigger it gets, the tighter we squeeze it in towards the center. All right, and then the minus 1 is what we call a phase shift. The 3 and the minus 1 together form something called a phase shift. And the phase shift moves it left and right, and then the b squeezes it in. So the 3x minus 1, that line is affecting the sine function. So again, if it were just x, it would look like that. But because it's not, then we're getting that altered version of the sine function. Now, what does the derivative tell us? The derivative tells us the slopes of the tangent lines. So it should make sense then, having something in there besides just x is affecting the tangent lines. So the chain rule shows us how it affects it. So what we have to do is treat this as if it were a variable, the 3x minus 1. Imagine if it were just x. What would be the derivative? So y prime. Okay. What this says is take the derivative of the outside. The derivative of sine, not worrying about the inside, the derivative of sine is cosine. Alright. But notice this is g of x. This is the same as it was before. We don't change the inside. So it's still 3x minus 1. Okay. And then what do? We chain on the derivative of what was inside. What was inside is 3x minus 1. That's a line. The derivative of a line is 3. Its slope. So the derivative of this line is its slope. Alright, so there's the chain rule. Now, the only thing we do here is we stick the chain out in front just because of neatness. It's not wrong to put it on the back end. It's just a more typical way to write it, to put the coefficients out in front of the functions. So what is this? This is the slopes of the graphs of this. Now, once again, to show you that it is, I'm going to say a equals negative 10. I'm going to let a go between negative 10 and 10. All right, and then we're going to use that tangent line notation. Y equals mx minus x1 plus y1. So m is the slope. Well, this is what I'm saying the slope is. So I'm going to grab this, but I'm just going to change the x to an a. Okay, now that's the slope. So again, all I'm doing here is y equals mx minus x1, a point on the graph, plus y1. Right? This is the point slope form of a line. It's just, that's what you typically think of the point slope form. Right? And we just added the y1 to both sides to put it over here, so the y equals can be by itself more than anything. Again, just for neatness. We do a lot of things in math to tidy things up. So this is all I'm doing. I'm just doing the point slope form. So this is my slope. This is the m. All right, x minus x1. I'm using a as the x coordinate, the known point. So I'm going to put x minus a. All right, and then plus y1. y1 is the y coordinate, this thing, when I plug a into it. So if I grab this, and then again just change that x, that x right there to an a, notice what I get is tangent line to this thing. All right, it's always tangent. Let me zoom in so we can see. But it's always tangent. And where is it tangent? It's tangent at the point a, comma, sine of 3x minus 1. Okay? Or sorry, 3a minus 1. But that's what's going on here. We are using the derivative to give us the slopes of the tangent line. That's what a derivative is. Right? If I forgot to do the chain, if I had left off the 3, it doesn't work. It's not tangent. Right? And that's not a tangent line. I need the chain rule to get the steepness correct. Okay, so the chain has to be chained on for this to actually be the derivative. Alright, so there's my answer. My dy dx is going to be 3 cosine, and then the inside stays the same. I just chain on the derivative. Alright, this one we got y equals the cube root of u squared. Alright, and then u is going to be the sine function. So that means I'm going to replace this u with the sine function. Alright, and square that. Okay, but I don't want to write it in that notation. So parentheses sine x, close parentheses, and then remember the roots and the powers can be written as a fractional power. So this is the 2/3 power. Okay, and now we have a power rule, and then the chain is the derivative of the inside. So again, think of this as just something to the 2/3 power. What's dy dx going to be? I bring the power down, so 2/3, parentheses, we leave the stuff inside alone, so the stuff inside is the sine function. We subtract 1 from the old power. The old power was 2/3. 2/3 minus 1 is negative 1/3. And I need to make that to the power of negative 1/3. Alright. That's the f prime with g on the inside. Okay. Then we multiply g prime. To that we multiply the derivative of sine. What's the derivative of sine? Once again, it's cosine. And then there is my derivative. Okay. I'm going to do the a trick again. So a equals, let's do negative 5. And we'll go between negative 5 and 4. That's all I have room for here in this picture. And I'm going to write y equals, again, I'm doing the slope. Let me write it down here what I'm doing. I'm doing mx minus x1 plus y1. All right, just the point slope form. My slope is the derivative. All right, I'm just going to change all those x's to a's. All right, I'm going to put a parentheses around this cosine since I'm going to multiply by something. I want to confuse Desmos, let alone you guys. All right, so that's the slope, that's the m, and then I'm going to do x minus x1. x1 is just a, what we're calling the variable, and then I'm going to add to it y1. y1 is given by the original function. All right, and then I'll add to it that with a being my my input. And then when I drag this around, notice I get those tangent lines. Okay, so that is the derivative. Those tangent lines slope are given by the derivative. So we've got the derivative right if we're seeing that on there correctly. All right, if we forgot to do the cosine, this is what a lot of people want to do here. They want to go ahead and take the derivative at the beginning. So they would basically they're doing f prime g prime and not chaining anything on. Well, you can see that that does not give us tangent line slopes at all. It's all wonky. Everything's messed up. Okay, so it's leave the inside alone, chain on the derivative. Oops, chain on the derivative, and now you've got your tangent lines. Okay, so that's the chain rule. We've got to leave the inside by itself alone, and then chain on the derivative of what was the inside function.